Alright, here's a solution for homework 1. Sorry for the background noise, it's really cold up here and I had to keep the heater on. So what we have this conveyor, the hanger for a conveyor system is extending outwards, and it's supported in 2 places. It has a load that varies from 600 to 3,800 pounds. So it doesn't reverse, it just is large and a little bit less, and then large and a little bit less. Okay. And we want to design this hanger for infinite life with a safety factor of 2 based on the modified Goodman criteria, and we want to specify the material and the structural shape as part of our answer. Okay, so I'm going to go ahead and write down on my piece of paper right here that you can't see it, but I'm looking at the screen here, and I'll draw this out right here so I can draw out what the assignment looks like. So I need to see what the screen is, and just make a pretty good drawing of the thing. It doesn't have to be perfect, but it would be nice to have it look pretty good. And I'll show you my drawing here in a second. Onto the thing, and little hash marks right in there. And put the dimensions that we're dealing with. Alright, so what is that? 24 inches and 36 inches. So 24 inches and 36 inches. Okay, and okay. So let me put up the camera here. Here is our arrangement right here, and I will put in my name. What this is Spring 21 ME470, and this is homework 1. So this is problem 1. And let me say what this thing is. This is a conveyor support. I will move this thing over here. No, not there. Not that. Okay, no, I'm going to keep that right there. Let me move the problem right over here. Let me take that out and bring it over to this screen over there. Okay, so now I can see the thing. And so what is this thing called? It's a hanger for a conveyor. So this is a hanger for conveyor. Conveyor. Okay, I spelled it right. And we have a load that's being applied right here. And so let's see, for the given, say load is 3,800, yeah, 600 to 3,800. 600, yep. 600 to, let's see, varies to 3,800 pounds. Okay, and find design for n good equal 2. Okay, so that's basically it. So where to begin? Well, loads is a good place. What kind of stresses are we dealing with here? Well, to me, that looks like it's going to be a bending load, right? And so this is like a simply supported beam. But how do we go about that? Well, let's make a free body diagram, right? So we have the FBD of this thing, and draw it out. And we have a load, and I'll just call this F for right now. And we're going to have a reaction right here. and we're going to have a reaction right here. But this is sort of a teeter-totter situation right here. If this load is going to have to stop it right from coming this way right there, prevent it right here. So and maybe I'll label these things. I'm going to call this A and this B, and we'll call that C. So let's call that force FC right here. So this is going to be the reaction at B, and this guy's going to have to go downwards to balance this out like a teeter-totter, right? So that reaction at RA is going to be right there, right? So and then these dimensions we could put in here lightly. 24 and 36 are happening onto this. So the sum of the force is sum of the moments. Sum of the moments. Let's go about A to start with. It's going to be equal to 0. Positive is going that way right there. So if we have negative, let's see, I think I just had my office hours. Want to know if I'm still there. I can go ahead and leave. Office hours are over with. So we'll go ahead and leave out of our office hours. Yeah, I don't care about my experience. Okay. So let's say that RB times 24, and then we're going to have a minus that FC. Let me keep that as a variable for just now. Okay, FC is going to be multiplied by 24 plus 36. Does that equal 60? Yes, I do believe it's 60. Equals 0. So RB is equal to FC 60 divided by 24. Right there. Okay. And then we could do the same thing. It depends on how I want to write this out. I think I want this RA also in terms of FC, because that FC varies between 600 and 3800. I didn't want to have to do this twice, so I'm leaving it as a variable. That's my thought process here. And I want to leave a shear moment diagram available underneath this right here. That's why I'm doing everything over to the right hand side. So I could also take the sum of the moments about B equals 0 right here. And so what we're going to find out is we take so this is going to be positive, right? So it's going to be RA, and that's going to be times 24, right? And then we're going to have a minus FC, and that's going to take times 36 right there, right? So what we're going to have here is RA is going to be equal to FC times 36 divided by 24. Okay. So in our shear moment diagram that we have as part of this right here, this is our shear, and here is going to be our moment, M. You will now have a shear that's negative directed there, boom. And that's going to be equal to our RA, and then you're going to have a shear that looks like this right here, and that's going to be equal to FC right there, right? And so now we're going to have a moment that's going to be that right to there, right? And you could either take it from this area right here, which is going to be RA times your 24, right? Or you could have your FC times your 36, right? To get this right here, because that's FC, right? Better be F equal to FC right in there. So honestly, you could probably have just jumped to a free body diagram by slicing through right to there, right? but because what you're going to level with right here is going to have FC times 36. Does that make sense? Right? FC times 36 is going to land right there. Because this is values FC, and the area down there is FC times 36. Or you could take this, which is going to be equal to 36 over 24 times FC, and multiply it by 24, and you end up with FC times 36. So that maximum moment, in terms of the max location, I want to be careful with the max, because we're about to have a fluctuating thing, and so we want to be careful with that. So anyway, M is going to be equal to FC times 36. So our M max is equal to 3,800 times 36. Which, by the way, my eyes aren't working very well right now. So that's 3,800 times 36, which is going to give me 136,800 inch-pounds. And then the minimum is going to be 600 times 36, or 600 times 36. And that's 21,600 inch-pounds. Okay? So these are the two moments between which this thing goes. So like when we go to, we want to have an alternating moment, and that's going to be the max minus the min over 2, right? So this minus that over 2. Alright, so let me do that. I get 79,200 inch-pounds. And then M mid-range, right, the mid-range moment is going to be M max plus M min divided by 2, or 136,800 plus 21,600 divided by 2. I'm cramming the thing in there. I shouldn't do that. 21,600 plus 2 divided. And I think I messed up the other one. I messed up the other one, yeah. This one I didn't subtract the 2, I added them. So, should know. 36,800 and 21,600 minus 2 divided. Yeah, I got 57,600. Should have shifted everything over to the side because I don't like to write into that margin if I can avoid it. Okay, so up to this point, this is the load section of the thing. We're going to have to now do something with the material. We're going to have to make a choice about our material. So I like to stick with Shigley if I can onto things. And what do I want to make this thing out of? Well, if you've had me for class before, you'll know that I'm partial to A36 steel because it's so very common. I wish Shigley included A36 as part of that. If I had something that was closer to A36 that's in Shigley, if we just want to have like some basic kind of steel, it would probably be the 1020 right here, right? So that's this guy right here. 1020 is a pretty basic steel, and you can see that here we have 30 KSI is the yield strength, 55 is the tensile strength. It's just a cheap steel, hot rolled type of thing. So I'm gonna that's the one that I decided to pick. right? So I'm going to write it down here. And I'm going to start on a fresh page because there's no reason to cram everything in there. And I wish I had used the page a little bit more effectively here. So this is 1 continued, and I will say that material is going to be 1020 hot rolled, where we have the yield strength, which we don't need because we're going to use Goodman, but that's okay. If we had Soderberg, we would need it. Is going to be 30 KSI, and the ultimate, this is what we're going to need, is going to be 55 KSI. Okay. So other things that we're going to have to do as part of this for fatigue, right? We're going to want to know we're going to get the endurance strength, right? So we go to the endurance strength thing, and we start off with that SE prime, right? So SE prime is going to be 0.5 times the ultimate strength, right? And then as we're making some of the corrections for this, the Marin correction factors, we're going to do as forged. Okay, so here's all the correction factors. We're going to leave the size alone, the size modification factor, because let's see, what do we don't know just yet how big this is going to be towards the thing. I'm probably going to use either a channel or an I-beam. I think for this, I'm probably going to go ahead and use a channel, right? I think a channel would work pretty well. You could use an I-beam. I kind of like the fact that a channel has a flat side to it. So that would like butt up against what looks like their pads. They're hanging down, but we're designing the thing so we could arrange how it's connected. We could have like some things drop down and have a bolt between there, so it allowed to bolt through the flange of the I-beam. We have some creativity as part of this, but we also may want to look and see what the standard is for the place that we're working at, so it'll be kind of similar to the other arrangements. We don't want to like go off to the side do too much. But this is really a simple type of arrangement, this hanger, so we don't necessarily need to make it exotic and very, very complicated. So I'm going to probably use a channel for the thing, but I don't know the size of it yet, so I'm going to go ahead and ignore that Marin factor, and I'm just going to pick out and adjust for the hot rolled. I'm going to pick hot rolled. We could do as forged too. We could do both and see what the result is going to be. I know for the people who are using the 11th edition, this is the 10th edition right here, you're going to have a slightly different value coming onto this thing. So anyway, I'm going to pick for that KA is going to be, I think in class I did the as forged, because this is going to be a channel and it's forged, so we'll go with that. So that's going to be 39.9. is that A, and then and you can't see what I'm writing down just yet, but I'll put it up there. And then the exponent is a negative 0.995, negative 0.995 right here. Okay, so back up to the stuff that we've done here. So move that over the side, and plugging those numbers in, 55 to the 0.995 negative. I raise it with that guy, and then 39.9 times there, and I get a 0.7401 as my factor. Remember that I said my SE prime was 0.5 times my 55, and I can't do that in my head. Seems like you should be able to, right? 27.5, that sounds right, 27.5 KSI. So we are going to assume all the other Marin factors are going to be 1 for now. And you might be questioning, well, how can you do that? Well, those are really estimates, right? Those are things that are estimating what the endurance strength is going to be of the material. Unless we had very specific things, we're not going to really know. We could refine the thing with it once we know the size, but we haven't picked the size out yet. And this is going to be good enough for right now. Whoops. Let me see what I do. I messed up. I can just multiply those two by each other. Okay. And so we get 20.35 KSI. That's good enough for now. Now we want to try to, this is going to be in bending, right? And so we have this Goodman. So now we have the ultimate strength, the endurance strength, and we have the alternating and mid-range moments. So we're going to want to put together the Goodman. I kind of trying to decide back and forth which way I want to write this. I'll go 1 over n, and I'm going to leave out the subscript for Goodman, is going to be sigma a over the S E plus sigma m over S U T, right? If you want to remember which one to divide through, remember this is an apples to apples thing. So the alternating and the endurance strength, those are the fluctuating ones right here. And the mid-range and the ultimate, those are the constant ones, right? So those are the reason why they get put into there. And so we know this. Okay, so let's take a look, and we want to say that the stress is going to be completely due to bending because of the nature of this problem. That's the only load that's on there. So we take MC over I, but this is a structural shape, and what we're trying to get is to find Z, right? So we're going to M over Z, which is the section modulus, right? We want to find a section modulus that's going to achieve the thing that we're asking to do. Okay, so what we can have here is to say 1 over n is going to be equal to MA over Z SE plus MM over Z SUT, right? Now let's do a little bit of manipulation right here. We're going to find a common denominator for this. I guess I'll write the thing out. We can go MA times SUT plus MM times SE divided by Z SE SUT. So what we could say now is we could bring that Z out to the side right here. MA SUT plus MM SE divided by safety factor right there. Nope. Bad math. Multiplied by safety factor, right? Divided by SE over SUT. Right. So let's see. Make sure we get all these units and stuff right. I think I can go ahead and use KSI for those as long as I have KSI here. Is that true? I'm a little nervous. About doing that because this is a KSI multiplied by KSI, and I'm going to go ahead and work the whole thing through doing no. Yeah, I'm just going to go ahead and use my actual units. So I'm going to go, I'm just too nervous to do it. 20, no, not 20. I'm looking at the wrong one right here. I want to have, this guy is my alternating, right? It's my alternating. So 57,600 times my ultimate is 55,000 plus my mid-range is 79,200 times my SE, which we found out to be 20,350. All of that multiplied by 2. And then down here, the 20,350 times my 55,000. And these units should be an inch cube right here, inch cube. And I'm turning that thing sideways. Maybe I should turn my camera so it's like right there. Oh, look, it's going, it's not focusing. Focus. That's what people yell at me all the time. Focus. Focus. All right. Enough with the weirdness. 57,600 and 55,000. Multiply that, and then 79,200 and 2350 times. We add those two together, and then 2350 divided 55,000 divided. I can't remember if I put the 2 in there or not. I think I didn't. I think I forgot to put the 2 in there. I'm gonna have to check again. So I get multiply by 2, 8.541 inches cubed. But I'm not confident. I think my mind wandered as I was putting the numbers in there. So I'll check again. So it's 57,600 multiplied by 55,000. Boom. 79,200. And multiply by 20,350, boom, add them together, divide by 20,350, divide by 55,000, yes, and then I need to multiply by 2. So that's the minimum section modulus that I require for this for this loading scenario. So let me see, I will come up to here. We'll come up to here, boom. Nope, one of these will be on the same side. I will come up to here, and this is ME470, yes. So useful links and resources, and I'll go to the structural section properties, and I decided in engineering the edge right here that I am going to use a channel, and the first one that defaulted up here was a 10-inch channel. That's 15.3 pounds right there. And so if you take a look about the x-axis right there, that is showing, and this is very small, I know, on your screen, but it shows that to be 15.9. Now, when you're thinking about the proportions of this thing, it's like 2 feet by 3 feet. Do you want 10 inches as a, yeah, that doesn't seem too, well, yeah, okay, so you see a C10. That's kind of large, right? That's pretty large on the thing, but I guess the loads that are on there are pretty substantial. I don't know. Well, we can make it a little smaller than this. And this is useful because, but I actually prefer if I could find a table, but I don't have a very good one. Let's take a look. Let's make it like 8 inches. Sounds like it might be pretty good. But then you'll see that we have 13.9. That's no. It's 11. Right? You have to look. You have to read this carefully. Even though we're using Z, they mean something different. So you need to use. You know, you always got to be careful and double check these that you're looking at the right thing. If you read down in here, you can see that this is that SY or SX is the elastic section modulus, whereas the ZX and ZY are the plastic section modulus. And you're like, oh, what is that? Well, your Google isn't broken, so you look it up and you find that the plastic section modulus is some other thing when the thing's already been like plastically deformed. That's not what we're doing. We're dealing with the elastic stuff. So we need to use the capital S here. I know they're using a different symbol than us, but that doesn't mean that we can't like think our way through there. So we're going to use the elastic section modulus, and it's going to be about the x-axis for us, because that's the way that we're going to arrange this thing. And so we look here, we get 11. Okay, so that's like an 8-inch size. 8-inch seems like it's a pretty good, but that's the thickest one that they have for the 8-inch. So let's maybe, let's check out with this, the largest one for the 6-inch. Is that going to be big enough for us? And that's not big enough. So we're probably going to have to stick with an 8-inch, but we don't need more. And 7 inches seems weird to me. So let's take a look at maybe the smallest 8-inch. And the smallest 8-inch has 8.14 is this section modulus about the X. And so that's just a little, not quite enough. So let's do a little bit larger right here. And so now we have a 9.02, right? 9.02. So the section that I'm going to select is going to be a C8 by, that's 13.7. By the way, that second number is the pounds per foot, I think. Yeah, pounds per foot. Not pounds per inch, that'd be a lot, pounds per inch. Pound per foot. That's just the way that they designate the thing. So they give you the C, it's a C channel. The 8 is close to being the depth of the thing. You can see the D is equal to 8 right here. And so I will write that thing out right there. So that's got an 8-inch depth to it. Its flange width is the BF. And my eyes aren't working. It looks like it says 2.34. So that's 2.34 is the size of this thing. And I should write out the section modulus onto this is 9.02 inches cubed right there. Okay. So in terms of our design, right? So we might want to draw the thing out, right? So I have instructed you, that's what you should do, is you should make a sketch of this thing. And so my idea for it is that, you know, we would have a connection right here that's being made is going to be lapped up like against like that right there, right? So the bolts would be coming through here and here's the pad that's being attached to this thing, and then it also would come up again. That's the reason why I chose C, is because it's something I could bolt up flat up against this thing, and also as I cantilevered the thing out. So I'm not going to draw the sketch of the thing, but I was trying to explain to you what we're going to do. We're basically, for the design in this case, the answer is going to be, so we only really need the material right there, is we're going to say AISI 1020 hot rolled steel for a C 8 by 13.7 channel right there. And that is the specification and therefore the design that we're going to submit and say this is the one that we think will survive according to the criteria. So let me see how much time that this took. That was 33 minutes to do this design. Hopefully it doesn't take you more than an hour to work through this and make some of those decisions. I will maybe make a separate video for problem 2. All right, so I'll be done.